Absolute zero is not simply the coldest place anyone could ever stand. It is not a location in space, and it is not a temperature that can be reached by ordinary cooling. Absolute zero is a fundamental boundary written into the laws of physics themselves. It is the point where thermal motion reaches its lowest possible value. When matter approaches this limit, all the random jiggling and vibration that we normally associate with heat fades away. At everyday temperatures, atoms shake and molecules spin and collide. In a warm room, trillions of particles crash into each other every moment, carrying energy in the form of motion. As the temperature drops, that motion slows. As it slows, the energy stored in those movements drains away. At 0 Kelvin, that thermal energy is as low as it can possibly go. There is no more heat to remove, yet something strange remains. Even when all thermal motion has been removed, matter is not perfectly still. This is one of the deepest discoveries of modern physics. At the smallest scales, the universe does not allow absolute stillness. Every particle is governed by the uncertainty principle, which says that you can never know both where a particle is and how fast it is moving with perfect precision. Because of this uncertainty, a particle can never sit completely motionless. Even at absolute zero, electrons still quiver inside atoms, and atoms themselves still carry a subtle, restless energy. This leftover activity is called zero-point energy. It is not heat, it is not temperature, it is a kind of built-in motion that cannot be removed without destroying the particle itself. This means that absolute zero does not create a frozen statue of matter, it creates a quantum active state, where everything that can move thermally has stopped, but everything that must move by the rules of quantum physics continues to do so. Even empty space is not truly empty. The vacuum itself is filled with fluctuating fields and fleeting particles that pop into existence and vanish again. These fluctuations exist even when the temperature is 0 Kelvin. The universe never becomes silent, it only loses its warmth. There is another reason absolute zero can never be reached. The third law of thermodynamics tells us that as a system gets colder, it becomes harder and harder to remove the remaining heat. Each tiny drop in temperature requires more effort than the last. The energy you can extract shrinks toward nothing, but never fully reaches it. You can approach 0 Kelvin endlessly, but you can never arrive. Absolute zero is a boundary that nature refuses to cross. This creates a powerful question. If temperature measures motion, and motion fades away as we approach absolute zero, what happens to forces that depend on energy? Does gravity weaken? Does it vanish? Does a frozen universe lose its ability to pull things together? To answer that, we must understand what gravity actually responds to. Gravity is not tied to warmth or cold. It does not care how fast atoms are moving. It cares about something far deeper. It cares about mass and energy and the shape of space-time itself. As matter cools, it loses thermal energy, but it does not lose its mass. A block of ice weighs the same as a block of steam, made from the same water. Cooling something does not remove the matter inside it. It only removes the energy of motion. Gravity comes from the presence of mass and energy together. The colder something becomes, the more its behavior changes, but its gravitational influence remains. This is why some of the coldest objects in the universe have some of the strongest gravity. Neutron stars are born hot, but over time, they cool. Yet, even when they become extremely cold, their gravity remains so intense that time itself slows near their surface. Black holes are even colder. Some of them are colder than the background temperature of the universe itself, yet their gravitational pull is unmatched by anything else. So absolute zero does not switch off gravity. It removes one form of energy, but leaves the deeper sources untouched. As we continue, we will see that cold matter behaves in a way that actually allows gravity to dominate even more strongly. As temperature falls, the familiar supports that hold matter up begin to disappear. In a normal star, the outward push that resists gravity comes from heat. Nuclear reactions in the core release enormous energy that keeps the gas expanding outward. The hotter the star, the harder it pushes back against its own weight. But as a star ages and its fuel runs out, that heat fades. The particles move more slowly. The pressure drops. Gravity gains the upper hand. What happens next depends on something far more subtle than temperature. It depends on quantum mechanics. When matter becomes extremely dense, the rules of everyday physics no longer apply. particles begin to obey a strange law called the Pauli exclusion principle. This law says that certain particles cannot occupy the same quantum state. In simple terms, it means that you cannot pack identical particles into the same place without forcing them into higher and higher energy levels. This creates a new kind of pressure that has nothing to do with heat. It is called degeneracy pressure. It exists even at 0 Kelvin. It arises because particles resist being squeezed into identical states. In a white dwarf star, this pressure comes from electrons. In a neutron star, it comes from neutrons. In both cases, the matter can be extremely cold, and yet the pressure holding the star up against gravity remains enormous. This leads to one of the most counterintuitive truths in all of physics. The colder an object becomes, the more gravity can dominate its structure. Without thermal motion to puff it up, matter collapses into a tighter and denser state. As it compresses, its mass remains the same, but its volume shrinks. Density rises. Gravity at the surface becomes stronger. This is why the densest objects in the universe are not hot clouds of gas, but cold, compact remnants. A white dwarf contains the mass of a star packed into a sphere the size of a planet. A neutron star contains the mass of the sun packed into a sphere only a few tens of kilometers across. These objects can cool to very low temperatures, but their gravity does not weaken. It grows more extreme. If even quantum pressure cannot resist the collapse, then matter falls inward without limit. This is how black holes are born. At that point, temperature becomes almost meaningless. The structure of space-time itself is overwhelmed by gravity. So as we approach absolute zero in any realistic system, we do not approach weightlessness. We approach a state where gravity has fewer and fewer forces opposing it. Heat disappears. Motion quiets. But mass remains. And where mass remains, gravity remains. This is why a universe that cools does not become empty of force. It becomes a place where gravity shapes everything more cleanly than ever before. In the next part, we will follow this idea to its ultimate conclusion and see how the coldest objects of all become the most powerful. When gravity is allowed to act without the support of heat, it reveals its true nature. In the deep cold of space, matter drifts together under its influence. Gas clouds collapse into stars. Stars exhaust their fuel and leave behind dense cores. Those cores cool over time, yet their gravitational pull never fades. Instead, it becomes sharper, more concentrated, and more dominant over everything around them. Black holes represent the extreme of this process. They are formed when gravity overwhelms every known form of pressure. Even the quantum resistance of particles fails. The result is a region of space-time so strongly curved that not even light can escape. What is remarkable is that black holes are also among the coldest objects that exist. Their temperature is given by what is called the Hawking temperature. For a massive black hole, this temperature can be far lower than the background temperature of the universe. These objects are colder than almost anything else, yet their gravity is unmatched. This tells us something profound. Gravity is not fueled by heat. It is not sustained by motion. It arises from the presence of mass energy and the structure of space-time itself. Even when all thermal energy has been removed, gravity continues to operate with full strength. The vacuum of space also plays a role here. Even when there is no matter and no heat, space itself is not empty. Quantum fields fill the vacuum, and they possess energy even at 0 Kelvin. This vacuum energy curves space-time and produces gravity. It may even be responsible for the mysterious dark energy that is pushing the universe to expand faster and faster. Temperature does not control this. Cold does not silence it. As the universe ages, it will continue to cool. Stars will burn out. Galaxies will drift apart. The background temperature will sink ever closer to absolute zero. But gravity will remain. Black holes will persist. Space-time will still bend and curve. Even in a universe that has lost all warmth, the geometry of reality will still be shaped by mass and energy. So when we ask what happens to gravity at absolute zero, the answer is not that it fades away. The answer is that it stands alone. When heat is gone and motion has quieted, gravity becomes the final sculptor of the cosmos. It is the force that endures when everything else has fallen silent. When people imagine gravity, they often picture something pulling downward, as if it were born from motion or pressure or some kind of invisible wind. But gravity is not created by movement, and it is not powered by heat. It comes from something far deeper and more permanent. It comes from mass and energy, shaping the geometry of space-time itself. This idea was revealed by Albert Einstein when he showed that matter tells space-time how to curve, and curved space-time tells matter how to move. Temperature is only one small form of energy within this much larger picture. Heat is a measure of how fast particles move. When atoms vibrate more strongly and molecules collide more violently, we say something is hot. When their motion slows, we say it is cold. But even when motion is removed, particles do not stop existing. Their mass remains, their rest energy remains, and that rest energy is the main source of gravity. A stone resting on the ground has almost no thermal motion compared to a flame, yet its weight is almost unchanged. Its gravity comes from the mass, locked inside its atoms, not from their warmth. Imagine a planet drifting through space. If it were suddenly cooled until it reached a temperature close to absolute zero, its gravity would remain almost exactly the same. The atoms would stop vibrating, but their nuclei and electrons would still carry mass. That mass would still bend space-time. Moons would still orbit. Objects would still fall toward its surface. Cooling removes motion, not matter. The same is true on the larger scales. Stars burn hot, but when they die and cool, they do not become weightless. A white dwarf star can be thousands of times cooler than it was in its youth, yet it still holds the mass of a star. Its gravity is so strong that a spoonful of its material would weigh as much as a mountain on Earth. That weight does not come from heat. It comes from how tightly matter is packed and how much mass is present. Neutron stars show this even more dramatically. These objects are formed when a massive star collapses under its own gravity. The core becomes so dense that protons and electrons merge into neutrons. The star shrinks to a sphere only a few tens of kilometers wide, yet it contains more mass than the Sun. Over time, neutron stars cool. They radiate away their heat into space. Some of them become extremely cold. But their gravity does not fade. In fact, it remains so intense that time itself runs slower near their surface. Light escaping from a neutron star is stretched by gravity, not by temperature. Even black holes fit this pattern. They are not hot furnaces of energy. The most massive black holes are actually some of the coldest objects in the universe. Their temperature is lower than the background glow left over from the Big Bang, yet their gravitational pull is so strong that it traps light and warps space-time into deep wells. Their coldness does not weaken them, it is irrelevant to their gravity. This tells us something fundamental about reality. Gravity is tied to energy, but not specifically to thermal energy. It responds to all forms of mass and energy, including rest, mass pressure, and even the energy of empty space. When something cools, it loses only the energy of motion. It does not lose the energy of being. As the universe ages, it continues to cool. The light from stars stretches and fades. The background temperature drops closer and closer to absolute zero. But gravity continues to guide the motion of galaxies and the growth of cosmic structures. In a young, hot universe, radiation once dominated the dynamics of space. In an older, colder universe, gravity takes over more completely. This is why cold matter behaves so differently under gravity. When particles are hot, they move too fast to easily collapse. When they cool, they settle. Clouds of gas in space only form stars when they are cold enough for gravity to pull them together. The cold does not weaken gravity. It allows gravity to work without resistance. As we move forward, we will see that this simple fact changes everything about how the universe evolves. When heat disappears, gravity becomes the most powerful sculptor of matter and space-time. As matter cools and thermal motion fades, gravity begins to reveal its full influence. In a hot gas, particles rush past each other at high speed. Their collisions create pressure that resists collapse. Gravity must struggle against this restless motion. But when temperature drops, that motion weakens. The particles drift more slowly. They spend more time near one another. Gravity has more opportunity to pull them together. This is why stars are born in cold regions of space. Giant clouds of hydrogen and dust float through galaxies for millions of years. While they remain warm, their particles move too quickly to allow collapse. But when these clouds cool through radiation, something remarkable happens. Gravity begins to dominate. The cloud fragments and clumps. Each clump falls inward and becomes denser. Eventually, the center grows hot from compression, and a new star ignites. Heat appears only after gravity has already done its work. This pattern appears everywhere in the cosmos. Cold gas forms galaxies. Cold dust forms planets. Cold matter forms compact objects. Heat is often the result of gravity, not its cause. When matter falls inward under gravity, it gains energy and heats up. The temperature we see in stars and planets is produced by gravitational collapse. This means that gravity does not need heat to exist. Heat often needs gravity to be created. Consider a white dwarf. It is the leftover core of a star that has exhausted its nuclear fuel. It no longer burns. It no longer generates heat. Over time, it cools and darkens. Yet its gravity remains powerful enough to pull material from nearby stars. It can even explode if it gains too much mass. None of this depends on temperature. It depends on mass and space-time curvature. The same is true for neutron stars. They too cool as they age. Some of the oldest neutron stars in the universe are extremely cold. Yet their gravity is still so strong that a teaspoon of their material would weigh billions of tons on Earth. Their pull on nearby objects is fierce. Their rotation bends space-time and drags it around with them. Cold does not weaken this. It has no effect at all. This reveals a deeper truth. Gravity is not a force that fades when motion stops. It is a geometric property of the universe. Space-time remains curved as long as mass and energy exist. Removing heat does not flatten space-time. It only removes one type of energy from the system. Even empty space itself is not free of gravity. The vacuum contains energy in the form of quantum fields. These fields fluctuate even at 0 Kelvin. Their energy curves space-time. This is why the universe expands and accelerates, even as it cools. Dark energy may be a manifestation of this vacuum energy. It is present regardless of temperature. So a universe at absolute zero would not be a dead flat void. It would be a place where matter, if any remained, would still attract matter. Black holes would still curve space-time. The vacuum itself would still drive expansion. Gravity would still be at work shaping the geometry of everything. As we approach the final part of this chapter, we will see how cold matter enters a realm where quantum mechanics and gravity intertwine. In that realm, heat becomes irrelevant, and the structure of matter is determined by deeper laws. When matter becomes extremely cold and extremely dense, the struggle between gravity and the quantum nature of particles becomes the dominant story of the universe. At this stage, heat has almost no role to play. The behavior of matter is no longer controlled by temperature, but by the rules that govern how particles are allowed to exist. These rules determine how far gravity can compress matter before something new happens. In white dwarfs, the resistance to gravity comes from electrons. They cannot all occupy the same state, so they push back when gravity tries to squeeze them closer together. This pressure exists, even at 0 Kelvin. It does not depend on heat. It depends on the structure of quantum states. In neutron stars, a similar pressure comes from neutrons. These particles also refuse to be forced into identical states. Their resistance to compression is immense, yet it too has nothing to do with temperature. But there is a limit. If enough mass is present, even these quantum pressures fail. Gravity wins. Matter collapses without bound. Space-time itself folds inward. A black hole is born. At this point, temperature is almost meaningless. The collapse is driven by geometry, not heat. Black holes themselves can be extremely cold. The more massive a black hole is, the lower its temperature becomes. Some black holes are colder than the background radiation of the universe. Yet their gravity is so strong that nothing can escape once it passes the event horizon. Their coldness does not weaken them. It simply means that they are not radiating much energy outward. This brings us to a powerful conclusion. Gravity does not fade as the universe cools. It becomes the dominant influence. When heat is gone, there is nothing left to resist the curvature of space-time. Matter, if it exists, is guided almost entirely by gravity and quantum laws. As the universe moves toward a colder and colder future, stars will fade and galaxies will drift apart. But gravity will still shape the remaining matter and the vacuum itself. Black holes will persist for unimaginable spans of time. Even when the temperature of the universe approaches 0, Kelvin space-time will still be curved by whatever mass and energy remain. So gravity is not something that depends on warmth. It is something that exists as long as the universe itself exists. Cold can quiet motion. It can still vibrations. It can bring thermal activity to a halt. but it cannot erase the weight of mass or the curvature of space. Gravity is not born from heat. It is written into the fabric of reality, and even at absolute zero, it remains. Cold matter does not behave the way our everyday intuition suggests. When we think of something cold, we imagine weakness and stillness, as if energy has been removed and only emptiness remains. But in the universe, the coldest forms of matter are often the most extreme and the most powerful. When heat disappears, matter does not become fragile. It becomes governed by deeper laws that allow gravity to shape it with extraordinary precision. In a warm cloud of gas, the particles rush in all directions. They collide and scatter and push against one another. This chaotic motion creates pressure. That pressure fights against gravity. It keeps the cloud spread out and prevents it from collapsing. But when the cloud cools, the motion slows. Collisions become gentler. The internal pressure drops. Gravity gains influence. What was once a loose fog of atoms becomes a slowly tightening mass. This is how stars are born. Great clouds of hydrogen drift through galaxies for millions of years. They glow faintly as they radiate away their energy. As they cool, they become more vulnerable to gravity. Eventually, a region becomes dense enough that gravity pulls it inward. The collapse accelerates. The center grows hotter from compression. Only after gravity has already built a dense core does heat return in the form of nuclear fusion. Cold opens the door, and gravity walks through. But this process does not stop when stars are formed. When a star exhausts its nuclear fuel, it loses its main source of heat. The outward pressure that once balanced gravity fades. The star begins to collapse. As it does, its matter is squeezed into ever smaller volumes. Temperature becomes less important than density. At these extremes, a new kind of pressure appears. This pressure comes from quantum mechanics. It arises from a rule called the Pauli exclusion principle. This rule states that certain particles cannot occupy the same quantum state. Electrons are among these particles. When gravity tries to force electrons closer together, they resist not because they are hot, but because they are forbidden from sharing identical states. This resistance creates electron degeneracy pressure. In a white dwarf, this pressure supports the entire star. A white dwarf may be cold and dark, but it contains the mass of a star, packed into a sphere about the size of a planet. Its density is immense. Its gravity is strong. The pressure that holds it up exists even at 0 Kelvin. It does not fade with cold. It is built into the nature of electrons. Neutron stars go even further. When a collapsing star becomes dense enough, electrons and protons combine to form neutrons. These neutrons also obey the exclusion principle. They generate neutron degeneracy pressure that resists gravity. A neutron star may cool over time, but it remains one of the densest and most gravitationally intense objects in the universe. A single spoonful of its matter would outweigh a mountain on Earth. The colder these objects become, the more gravity defines their structure. Without heat to push matter outward, everything is governed by the balance between gravitational compression and quantum resistance. This balance creates some of the most stable and extreme objects known to science. Cold matter under gravity does not drift apart. It settles into precise forms dictated by fundamental laws. It becomes white dwarfs, neutron stars, and eventually black holes. Heat once held matter up. Cold allows gravity to reveal its full power. As we move deeper into this story, we will see how quantum pressure and gravity engage in a cosmic struggle that determines the fate of stars and the shape of the universe itself. When gravity pulls matter inward and heat is no longer able to resist the collapse, the universe enters one of its most dramatic phases. This is the realm where quantum mechanics stands between stability and destruction. In this cold, dense state, particles are no longer free to move wherever they wish. They are locked into a tight quantum structure that defines how much pressure they can produce. In a white dwarf, electrons are the guardians against collapse. They fill the lowest available quantum states, and when gravity tries to compress them further, they are forced into higher states. This creates a powerful pressure that pushes back. It is not created by temperature. It exists even when the star is nearly at 0 Kelvin. This is why a white dwarf can remain stable for billions of years, as it slowly cools and fades. But this protection has limits. If a white dwarf gains too much mass, gravity becomes too strong for electron pressure to resist. The electrons are forced into such high energy states that they combine with protons. The star collapses further. A neutron star is born. Here, the pressure comes from neutrons themselves. These particles also obey the exclusion principle and resist being squeezed together. A neutron star is a laboratory of cold extreme physics. Its temperature may be low compared to its birth, but its density is beyond anything we experience on Earth. The matter inside it is packed so tightly that a single cubic centimeter could weigh billions of tons. Yet it does not collapse further because neutron degeneracy, pressure, and nuclear forces hold it up. Again, this resistance does not come from heat. It comes from the quantum nature of matter. As the star cools, its thermal energy fades, but its gravity remains, its mass remains, its curvature of space-time remains. The balance between gravity and quantum pressure defines its size and structure. Cold does not change this balance. It only removes the distractions of thermal motion. This tells us something essential about the universe. Heat is not what holds matter together. Heat is often what keeps it apart. When heat disappears, gravity and quantum mechanics take control. They shape matter into the densest stable forms that can exist. In the cold depths of space, this process plays out over and over again. Gas clouds collapse into stars. Stars collapse into white dwarfs or neutron stars. These remnants cool and darken, but they remain powerful because their mass and density are unchanged. Gravity continues to bend space-time around them and influence everything nearby. As we approach the final part of this chapter, we will follow this path to its ultimate conclusion, where even quantum pressure fails and gravity reigns alone. When even the strongest quantum pressures can no longer resist gravity, matter crosses a final threshold. This is the moment when a black hole is formed. At this point, electrons and neutrons can no longer support the weight of the star. The collapse becomes unstoppable. Space-time itself folds inward under the mass. A region appears from which nothing can escape. What is remarkable is that this process does not require heat. It requires cold. A collapsing star must lose its thermal energy in order to fall inward. As radiation escapes, the core cools. Pressure drops. Gravity takes control. The colder the core becomes, the easier it is for gravity to compress it further. In this sense, black holes are born from the quieting of heat. Black holes themselves are among the coldest objects that exist. Their temperature depends on their mass. The more massive a black hole is, the lower its temperature becomes. Some of the largest black holes are colder than the faint glow of the universe itself, yet their gravitational influence is overwhelming. They shape the motion of entire galaxies. This final stage reveals the true relationship between cold and gravity. Cold does not weaken gravity, it removes resistance. When heat is gone, there is nothing left to push matter outward. Gravity becomes the dominant sculptor of reality. In a universe that continues to cool, gravity will increasingly define the fate of everything that remains. Stars will die. Their remnants will cool. Black holes will persist. Even as temperature approaches zero, Kelvin space-time will still be curved by whatever mass and energy remain. Cold matter under gravity does not drift away. It settles into the deepest structures the universe can form. White dwarfs, neutron stars, and black holes are not powered by heat. They are powered by the geometry of space-time and the quantum rules that govern matter. This is why the coldest places in the universe are not empty. They are the most intense. They are the places where gravity speaks the loudest. When heat fades from matter, the universe does not become quiet. It becomes governed by deeper and more exact laws. Thermal motion is only one way energy appears. When that motion disappears, what remains is the raw structure of matter and the curvature of space-time. In this regime, gravity and quantum mechanics take center stage, and their interaction determines the fate of everything that exists. Gravity is always present. It does not weaken when particles slow down. It is created by mass and energy, shaping the geometry of space-time. Every particle bends the space around it. Every collection of matter creates a region of curvature that guides the motion of everything nearby. This bending of space is what we experience as gravitational attraction. Heat does not cause this bending. It only adds a small amount of extra energy to it. In a star, gravity pulls inward on every atom. When the star is young and hot, nuclear reactions in its core produce enormous energy. This energy makes the gas push outward. The pressure created by that heat balances gravity. The star exists in a delicate equilibrium between collapse and expansion. But when the fuel runs out, the heat begins to fade. The outward pressure weakens. Gravity gains the advantage. As the star cools, it contracts. Its matter is squeezed into a smaller volume. Density rises. Temperature becomes less important than how tightly the particles are packed. This is where quantum mechanics begins to dominate. Particles are no longer free to move as they please. They are forced into specific states, dictated by their wave nature. Electrons are one type of particle that obeys the Pauli exclusion principle. This principle says that two identical electrons cannot occupy the same quantum state. When gravity tries to force electrons into the same place, they resist by jumping into higher energy states. This resistance creates a pressure that pushes outward. It is called electron degeneracy pressure. It does not depend on heat. It exists even at 0 Kelvin. In a white dwarf star, this pressure supports the entire object. The star may be cold and dark, but its electrons still resist compression. The mass of the star is packed into a volume no larger than a planet. Its gravity is strong because its density is high, yet it does not collapse further because quantum mechanics holds it up. But even this pressure has a limit. If the star is massive enough, gravity can overwhelm electron degeneracy pressure. The electrons are forced so close to protons that they merge to form neutrons. The star collapses again. A neutron star is born. Neutron stars are held up by a similar pressure created by neutrons. Neutrons also obey the exclusion principle. They resist being forced into identical states. This neutron degeneracy pressure is even stronger than the electron version. It can support a star with more mass, but it too has a limit. As neutron stars cool, they lose thermal energy, but they do not lose mass. Their gravity remains immense. The curvature of space-time around them is so strong that it affects the flow of time. Clocks on their surface tick more slowly than clocks far away. Light climbing out of their gravity well is stretched to longer wavelengths. None of this depends on temperature. It depends only on mass and geometry. The colder these objects become, the more purely their structure is defined by the balance between gravity and quantum pressure. Heat once played a role in shaping them, but it is no longer needed. In the deep cold, the universe reveals that gravity and quantum mechanics are the true architects of matter. This is the stage on which the final acts of stellar evolution unfold. When even neutron pressure fails, gravity takes over completely. In the next part, we will follow that process and see how cold matter crosses the point of no return. When a star has collapsed into a neutron star, the universe has already entered one of its strangest regimes. Matter is no longer held up by heat. It is held up by the rules of quantum mechanics. The star may radiate away almost all of its thermal energy and become dark and cold, but its structure remains locked in place by the way particles are allowed to exist. In this state, gravity and quantum pressure are the only forces that matter. Inside a neutron star, the density is so high that atoms no longer exist. Electrons and protons have fused into neutrons. These neutrons are packed together so tightly that the distance between them is comparable to the size of the particles themselves. There is almost no empty space. Yet even in this extreme environment, the neutrons cannot all collapse into the same state. The exclusion principle forces them into a layered structure of quantum states. This creates an enormous outward pressure that balances gravity. This pressure is not heat. The neutrons are not moving violently. They are not hot. They are locked into a cold quantum configuration. Their resistance to compression comes from the fact that their wave nature forbids them from overlapping in the same way. Even if the star were cooled to absolute zero, this pressure would remain. But gravity is relentless. If the mass of the neutron star is large enough, even neutron degeneracy, pressure, and nuclear forces cannot stop the collapse. There is a tipping point where no known form of matter can provide support. At that moment, the star crosses a threshold in space-time. The curvature becomes so extreme that it traps everything inside. This is the birth of a black hole. It is not an explosion. It is not a fiery event. It is a quiet surrender of matter to gravity. The star loses its last ability to resist compression. Space-time folds inward. An event horizon forms. Beyond that boundary, the future leads only deeper inward. The remarkable thing is that this process is driven by cold. A collapsing star must radiate away its heat. in order to shrink. The more energy it loses, the more gravity can compress it. In this sense, black holes are born not from heat, but from the disappearance of heat. Once formed, a black hole continues to cool. Its temperature is determined by quantum effects near the event horizon. The more massive the black hole is, the lower its temperature becomes. The largest black holes in the universe are colder than the faint radiation that fills space. They absorb more energy than they emit. They grow colder as they grow larger. Yet their gravity is immense. They bend space-time on scales that can influence entire galaxies. Stars orbit them, gas falls into them, light curves around them. Their coldness does not weaken them. It is simply a sign that they are not releasing much energy. This reveals something fundamental about the universe. Gravity is not tied to warmth. It is not powered by motion. It is powered by the presence of mass and energy shaping space-time. When heat disappears, gravity becomes more pure. It acts without interference. As the universe ages and cools, gravity will continue to shape what remains. Matter will become locked into black holes and other cold remnants. The background temperature will fall closer and closer to 0 Kelvin. But space-time will not become flat. It will remain curved by whatever mass and energy still exist. In the deepest cold, gravity does not fade. It stands alone. It becomes the last force shaping the destiny of matter and the structure of reality itself. When the universe reaches its coldest and quietest stages, gravity does not step aside. It becomes the dominant storyteller of everything that still exists. By this time, most stars have already lived and died. Their light has faded. Their heat has been radiated away into the vastness of space. What remains are the cold, dense remnants of once brilliant objects and the invisible geometry of space-time that binds them together. Black holes persist long after ordinary matter has cooled. They may be colder than the background of the universe, yet their gravity continues to influence everything around them. A black hole does not need heat to pull matter inward. It needs only mass and space-time curvature. Even in a universe approaching 0 Kelvin, these objects remain the anchors of structure. Around them, particles drift slowly through space. Without thermal energy to push them apart, gravity guides their motion. Gas clouds that once glowed with heat may have long since fallen into black holes or dispersed into the vacuum. But the geometry of space still tells every remaining particle how to move. Quantum mechanics continues to play its quiet role. Even in the coldest vacuum, fluctuations persist. Fields tremble. Energy flickers in and out of existence. This vacuum energy still curves space-time. It still contributes to the overall gravitational landscape of the universe. Absolute zero does not erase this restless background. It cannot. Over unimaginable spans of time, black holes themselves will eventually evaporate through a process called Hawking radiation. This radiation is extremely weak and extremely cold. It takes longer than 10 to the power of 67 years for a stellar mass black hole to disappear. For supermassive black holes, the timescale is even longer. These are some of the longest-lived structures in the universe. During all of this, gravity remains. As black holes slowly lose mass, space-time gradually changes shape. The curvature they create becomes weaker, but it never vanishes completely until the mass is gone. Even then, the vacuum energy of space remains. This means that even a universe that has lost all ordinary matter and all heat will not be a simple flat emptiness. It will still have a gravitational character set by the energy of the vacuum. Space-time will still expand. It will still curve. It will still have a structure. So gravity is not something that belongs to stars or heat or motion. It belongs to the universe itself. It is woven into the way space and time exist. Cold can strip away motion. It can erase light. It can quiet the cosmos. But it cannot remove the geometry of reality. When everything else fades, gravity remains as the final expression of the universe. In the depths of space where light has little meaning and warmth has nearly vanished, there exist objects that are colder than almost anything else in the universe. These objects are black holes. They are often imagined as burning infernos or violent storms of energy, but in reality, the largest black holes are profoundly cold. Their temperature is lower than the faint glow that fills the cosmos, yet they possess the strongest gravity that nature allows. A black hole forms when gravity compresses matter beyond every known limit. A star collapses under its own weight. and no force can stop the inward fall. Space-time itself bends so deeply that a region appears from which nothing can escape. This boundary is called the event horizon. Once something crosses it, there is no path back out. Not even light can return. Despite this power, black holes are not hot. They do not radiate heat in the way stars do. Instead, they have a very faint temperature that comes from quantum effects near the event horizon. This temperature is called the Hawking temperature. It arises because the vacuum of space near the horizon is not truly empty. Quantum fluctuations create pairs of particles. One can fall into the black hole while the other escapes. To an outside observer, this looks like radiation coming from the black hole. The key point is that this temperature is inversely related to the mass of the black hole. The more massive a black hole is, the colder it becomes. A black hole with the mass of the Sun is already far colder than deep space. A supermassive black hole with millions or billions of times the mass of the Sun is even colder. Some of these giants are colder than the background radiation left over from the Big Bang. This means that black holes are not only the strongest gravitational objects in the universe, they are also among the coldest. This is the opposite of what many people expect. It shows that gravity and temperature are not linked in a simple way. Extreme gravity does not require heat. In fact, the most gravitationally dominant objects can be nearly at 0 Kelvin. In these cold giants, gravity is pure. There is almost no outward radiation. There is no thermal pressure pushing matter away. Everything that comes near is guided almost entirely by space-time curvature. Gas falls inward. Stars are torn apart. Light bends around the event horizon. All of this happens in an environment that is colder than the surrounding universe. This reveals a deep truth. Cold does not weaken gravity. It allows gravity to express itself without interference. When heat fades, gravity stands alone as the ruler of motion and structure. As we move further into this chapter, we will explore how the cold nature of black holes changes the fate of the universe and what happens to them as time stretches toward infinity. Black holes exist in a strange balance between gravity and quantum physics. Even though they are incredibly cold, they are not completely silent. Their faint Hawking radiation slowly carries energy away into space. This radiation is extremely weak for large black holes. It is so weak that for billions of years the black hole actually gains more energy from the surrounding universe than it loses. Only when the background of space becomes colder than the black hole does evaporation begin to dominate. As the universe expands, it cools. The light from distant galaxies stretches and fades. The cosmic background temperature drops closer and closer to 0 Kelvin. Eventually, even the coldest black holes will be warmer than the surrounding space. At that point, they will slowly begin to lose mass through Hawking radiation. This process is unimaginably slow. A black hole with the mass of the Sun will take around 10 to the power of 67 years to evaporate. A supermassive black hole will take far longer. During this long era, gravity still rules. Black holes continue to pull matter inward. They continue to curve space-time. Their coldness does not stop them from shaping their surroundings. In fact, because they radiate so little energy outward, there is almost nothing to oppose their gravitational pull. As a black hole shrinks, its temperature rises. A smaller black hole is hotter. But for most of its life, a large black hole is nearly at 0 Kelvin. It exists as a cold gravitational engine, slowly exchanging energy with the vacuum. This leads to a remarkable picture of the far future. Stars will be gone. Galaxies will have drifted apart. Ordinary matter may decay. What remains will be a scattering of black holes embedded in a cold, dark vacuum. These black holes will be the last massive structures in the universe. They will dominate the geometry of space-time. Even as they slowly evaporate, gravity continues to shape their final moments. The energy they release goes into the vacuum. It changes the curvature of space. Nothing in this process depends on heat in the way we normally understand it. It depends on quantum fields and space-time geometry. Black holes show us that cold and gravity are not opposites. They are partners in the deepest workings of the cosmos. When everything else fades, these objects remain as the cold anchors of reality. As black holes slowly lose mass through their faint radiation, the universe enters an era that is colder and darker than anything that came before. The background temperature continues to fall. As space expands, light stretches into longer wavelengths, Energy becomes ever more dilute, yet gravity never vanishes. It continues to shape the behavior of whatever remains. A black hole does not simply disappear when it evaporates. It releases its mass as energy into the vacuum. This energy still curves space-time. The geometry of the universe responds to it. Even when the last black hole has faded, the vacuum itself still contains energy in the form of quantum fields. This vacuum energy may be what drives the expansion of the universe. It is present even at 0 Kelvin. This means that the coldest possible universe is not empty. It is filled with invisible fields and subtle gravitational effects. Space-time continues to evolve. The shape of the universe continues to change. There is no moment when gravity switches off. Black holes therefore serve as a bridge between matter and the vacuum. They show how mass energy can be transformed into pure space-time structure. Their coldness is not a sign of weakness. It is a sign that they are not losing much energy. They persist, quietly shaping their surroundings for unimaginable lengths of time. When we think about absolute zero, it is tempting to imagine a frozen static universe. But black holes reveal a different truth. Even when everything is cold, gravity remains active. It bends space. It guides motion. It determines the fate of whatever exists. So the coldest objects in the universe are also the most powerful. They remind us that temperature measures motion, but gravity measures existence. When motion fades, existence remains, and gravity continues to write the story of the cosmos. Absolute zero has always sounded like the end of everything. The phrase itself carries a sense of finality, as if reality reaches a wall and nothing can exist beyond it. Yet in physics, absolute zero is not a cliff. It is a doorway. It is the point where the most hidden and powerful layers of the universe become visible. When temperature falls to 0 Kelvin, the familiar world of heat and motion fades away, but something far deeper takes its place. Temperature is not a measure of how much energy exists. It is a measure of how that energy is moving. When something is warm, its particles vibrate, rotate, and collide. When something cools, those motions slow. As a system approaches 0 Kelvin, all thermal motion disappears. Molecules stop spinning, atoms stop jiggling. The chaotic dance of heat comes to an end, but this does not mean the universe becomes still. At the heart of modern physics lies a rule that prevents perfect stillness. It is called the uncertainty principle. This principle says that no particle can ever have both a perfectly known position and a perfectly known motion at the same time. Because of this, a particle can never be completely at rest. If it were, its position and motion would both be fixed, and that is forbidden by the laws of nature. So even when all heat is removed, particles still move in a subtle and unavoidable way. Electrons continue to quiver inside atoms. Atoms themselves retain a faint vibration. This leftover motion is called zero-point motion. It is not heat. It is not temperature. It is the minimum activity that reality allows. If this motion were somehow removed, the particle would not become colder. It would cease to exist. Zero-point motion is the heartbeat of matter, but even this is not the deepest layer. The most astonishing truth about absolute zero is that it does not make the universe empty. Even if every atom were removed from a region of space, even if every particle of matter and every photon of light vanished, something would still remain. The vacuum itself would still be there, filled with invisible energy and restless activity. Empty space is not empty, it is filled with quantum fields. These fields are not objects floating in space, they are the very fabric of space. Every type of particle corresponds to a field that exists everywhere. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. Even when there are no ripples, the fields themselves remain. These fields can never be perfectly still. The uncertainty principle applies to them as well. Even in their lowest energy state, they must fluctuate. Tiny waves ripple through the vacuum. Pairs of particles briefly appear and vanish. Energy flickers into existence and fades again. This restless activity is called vacuum fluctuation. It is not heat. It does not make space warm, but it is real energy. This energy has measurable effects. It can push metal plates together in the Casimir effect. It can shift the energy levels of atoms. It can influence how light moves through space. Most importantly, it has gravity. Einstein showed that gravity is not a force pulling things through space. It is the curvature of space-time itself. Mass and energy tell space how to curve, and curved space tells matter how to move. Anything that carries energy bends the geometry of the universe. The vacuum carries energy. That means the vacuum bends space-time. Even a universe with no matter and no radiation would not be flat. Space itself would still have a shape. Time would still have a flow. The vacuum would still curve the cosmos. This is believed to be the origin of dark energy, the mysterious influence that causes the expansion of the universe to accelerate. Dark energy does not behave like ordinary matter. It does not thin out as space expands. It appears to be a property of the vacuum itself. As the universe grows, there is more vacuum, and therefore more dark energy. The expansion speeds up. This leads to a profound conclusion. As the universe cools and all ordinary forms of energy fade, the vacuum becomes dominant. Heat disappears. Light stretches away. Matter decays. But vacuum energy remains. Its gravitational influence grows as space grows. So at absolute zero, gravity does not vanish. It becomes more important than ever. In the distant future, the universe will be cold beyond imagination. The background temperature will approach 0 Kelvin. Stars will be long gone. Even black holes will eventually fade, yet space-time will still curve. The vacuum will still fluctuate. Expansion will continue. Absolute zero is not the death of the universe. It is the moment when only the deepest forces remain. When heat and motion have vanished, what is left is the geometry of space and time and the silent, restless energy of the vacuum itself. When the universe is stripped of almost all heat and light, what remains is not emptiness, but a vast and subtle ocean of energy that cannot be removed. This ocean is the vacuum itself. It fills every region of space, and it exists even when nothing else does. As temperature falls towards 0 Kelvin, the vacuum becomes the most important component of the cosmos, because every other form of energy fades while it remains. To understand why the vacuum never disappears, it is important to understand what a quantum field is. A quantum field is not something that sits inside space. It is something that defines what space is capable of. Each field is a set of values at every point in space that tells particles how they may exist. Even when there are no particles, the field still has a value. It still possesses energy. The lowest energy state of a field is called its ground state. But this ground state is not zero. The uncertainty principle forbids a field from having no energy at all. There must always be a minimum amount of vibration. These vibrations are the vacuum fluctuations that fill space. If one could cool a region of space to absolute zero, the matter inside, it would lose its thermal motion, but the vacuum would still fluctuate. Those fluctuations are not created by temperature. They are created by the fundamental structure of quantum reality. These fluctuations have gravity. Every flicker of energy bends space-time a tiny amount. Taken together across the entire universe, they create a smooth but powerful gravitational effect. This effect may be what we observe as dark energy. Dark energy behaves in a way that is deeply strange. Unlike matter and radiation, it does not dilute as space expands. Its energy density remains constant. This means that as the universe grows, there is more total dark energy. Its gravitational effect becomes stronger. This leads to a future where the universe becomes emptier and yet more dominated by gravity in this vacuum form. Galaxies drift apart, stars burn out, radiation fades, but the vacuum remains, and its energy shapes the expansion of space. So absolute zero does not lead to a static universe. It leads to a universe where the only remaining motion comes from the geometry of space-time itself. In a universe that has cooled so deeply that almost all thermal motion has vanished, the vacuum becomes the true stage on which reality continues to unfold. Every particle that still exists drifts through a sea of invisible fields. Even if matter were to disappear entirely, those fields would remain. They would still fluctuate. They would still contain energy, and that energy would still curve space-time. The expansion of the universe is driven by this vacuum energy. It is a form of gravity that works not by pulling matter together, but by stretching space apart. As the cosmos grows older and colder, this effect becomes stronger relative to everything else. Matter thins out. Radiation loses energy. but the vacuum stays the same. This creates a future where every remaining structure becomes isolated. Regions of space slip beyond one another. Horizons form that no signal can cross. The universe becomes a collection of lonely islands drifting through an ever-expanding sea. Yet even in this extreme cold, gravity remains. It has simply changed its role. Instead of building stars and galaxies, it now controls the fate of space itself. So when temperature reaches 0 Kelvin, gravity does not disappear. It becomes the defining feature of existence in the far future of a universe that has cooled toward absolute zero. The vacuum becomes the true substance of reality. What once seemed like empty space reveals itself as the most enduring and powerful presence. Long after stars have burned out and galaxies have drifted beyond one another, the vacuum remains filled with restless energy and subtle motion. This energy is not heat. It does not warm anything, yet it is real, and it carries gravitational influence that shapes the fate of everything that still exists. To understand why the vacuum never goes quiet, it helps to imagine what a quantum field really is. A quantum field is not something that floats inside space like a cloud. It is a description of what space itself is allowed to do. Every point in space is associated with a value for each field. These values define the potential for particles to exist and interact. Even when no particles are present, the fields remain. They are part of the structure of reality. Because of the uncertainty principle, these fields can never be perfectly still. If a field were to have no motion and no variation, it would have a perfectly defined value everywhere. That would violate the uncertainty principle, which requires that there must always be some degree of fluctuation. These fluctuations are the vacuum energy that fills space. This energy does not disappear when temperature falls. Cooling removes thermal motion from matter, but it cannot remove the fundamental jitter of the fields themselves. The vacuum continues to ripple with activity even at 0 Kelvin. This means that there is always some energy present everywhere in the universe. Gravity responds to this energy. According to Einstein, energy and mass curve spacetime. They tell space how to bend and time how to flow. Because the vacuum has energy, it also has gravity. It contributes to the overall shape of the universe. In the early universe, matter and radiation dominated the gravitational landscape. Stars formed, galaxies assembled, structures grew. But as the universe expanded, these forms of energy thinned out. Matter spread over larger volumes. Radiation lost energy as its wavelengths stretched. Their gravitational influence weakened. The vacuum did not weaken. Its energy density stayed the same. As space grew, there was more vacuum and therefore more vacuum energy. This created a gravitational effect that became stronger relative to matter and radiation. This effect is what we call dark energy. It causes the expansion of the universe to accelerate. As the cosmos cools toward absolute zero, this vacuum-driven gravity becomes the dominant force. The universe does not slow down into stillness. It speeds up into a colder and emptier state. In this future, any remaining particles of matter drift farther apart. Galaxies that were once bound together are carried beyond each other's reach by the expansion of space. Eventually, every region of the universe becomes isolated. No signal can cross the growing gaps. Even light cannot travel fast enough to keep up. Yet gravity remains active. It is no longer gathering matter into stars, but it is shaping the global geometry of spacetime. The universe continues to evolve, even when it is almost completely cold. Time also continues. Even without heat, there is change. The expansion of space provides a direction. The vacuum energy provides a driver. The future continues to unfold. So absolute zero does not bring an end to reality. It brings an era where only the deepest layers of physics remain. Quantum fields fluctuate. Space-time curves. The universe grows larger and colder. This is the quiet destiny of a cosmos ruled by the vacuum. A place without warmth, but not without motion. A place where gravity is no longer the pull of stars, but the slow stretching of space itself. In the final era of the universe, when temperature has fallen so close to absolute zero that even the faint background glow of ancient radiation has nearly disappeared, the cosmos enters a state that is both empty and yet deeply alive. There are no stars to shine, no galaxies to light the darkness, and no warmth to move matter through space. But this is not the end of reality. It is the moment when gravity and the vacuum become the only remaining architects of existence. The vacuum is not nothing. It is a vast ocean of quantum fields that exist everywhere at once. These fields do not depend on matter to exist. They do not require light, heat, or particles. They are woven into the fabric of space itself. Even when the universe has been stripped of everything else, these fields remain, quietly fluctuating, because the laws of physics forbid them from becoming perfectly still. Every quantum field has what is called a ground state. This is the lowest energy state it can have. But this lowest state is not zero. The uncertainty principle ensures that there must always be some residual energy. That energy appears as tiny fluctuations in the vacuum. Particles momentarily emerge and disappear. Fields tremble. Energy rises and falls in an endless, invisible dance. This vacuum energy is what gives the universe its final gravitational character. According to Einstein, energy tells space-time how to curve. It does not matter whether that energy comes from a blazing star or a silent quantum field. If energy exists, it bends the geometry of space and time. Because the vacuum contains energy, the vacuum has gravity. In the far future of the universe, when all ordinary matter has decayed and black holes have evaporated, this vacuum gravity becomes the dominant force. It does not gather matter into structures because there is almost no matter left. Instead, it governs the expansion of the cosmos itself. Space continues to stretch. Distances grow. Regions of the universe drift apart forever. This expansion is not driven by heat. It is driven by the vacuum. Dark energy, which is believed to be a manifestation of vacuum energy, does not fade as the universe cools. It remains constant per unit volume of space. As space expands, there is more vacuum and therefore more dark energy. The expansion accelerates even as the universe becomes colder and emptier. This leads to a strange and beautiful future. The universe becomes vast beyond imagination. Any remaining particles are separated by distances so great that they will never meet again. Light cannot cross the expanding gaps. Each region becomes its own isolated island of reality. Yet all of this is guided by gravity in its vacuum form. Time continues to flow in this cold universe. There is no heat to measure, no clocks ticking in the usual way, but the expansion of space itself provides a direction of time. The universe is still changing. The future is still different from the past. Gravity and the vacuum keep the story moving. So what happens to gravity at absolute zero? It does not vanish. It does not weaken. It transforms. When heat is gone and matter is gone, gravity becomes the geometry of space-time shaped by the vacuum. It becomes the quiet force that guides the final evolution of the cosmos. This is the deepest answer to the question of cold and gravity. Absolute zero does not erase the universe. It reveals its most fundamental form, a universe of curved space, fluctuating fields, and silent but unstoppable expansion. When people hear the phrase absolute zero, they imagine a universe that has reached the end of all change. The words seem to imply that motion has stopped, that nothing can happen anymore, and that time itself might as well have frozen. But physics does not agree with this picture. Even when temperature falls to 0 Kelvin, the universe does not become simple. It becomes more subtle, more deeply structured, and more dominated by information than ever before. To understand why this is so, we must look beyond heat and into the meaning of entropy itself. Entropy is often described as disorder, but that description hides its true nature. Entropy is not chaos. It is a measure of how many different microscopic configurations can give rise to the same macroscopic appearance. In other words, entropy measures how much information is hidden beneath what we see. A glass of water looks calm and uniform, but on the inside, its molecules are moving in countless ways. The more possible ways those molecules can be arranged, the higher the entropy of the water. When something is warm, its particles have many possible positions and velocities. They can move in countless patterns. That means the system has high entropy. When something cools, the number of possible arrangements decreases because the particles lose energy and settle into lower energy states. It feels natural to assume that when temperature reaches 0 Kelvin, all entropy must vanish. But quantum mechanics shows that this is not true. At 0 Kelvin, particles do not collapse into a single rigid configuration. The uncertainty principle forbids that. A particle can never have both a perfectly defined position and a perfectly defined motion. Because of this, even in the lowest possible energy state, there must be some spread in its quantum state. This spread creates multiple possible configurations that all have the same minimum energy. This means that even at 0 Kelvin, a system can have entropy. This is called residual entropy. It comes from the fact that there may be many quantum states that are equally allowed. The system does not know which one it occupies. That uncertainty is information, and information is entropy. A perfect crystal cooled to 0 Kelvin may still have its atoms arranged in slightly different patterns that all cost the same energy. Those patterns are invisible to us, but they are real. The crystal carries hidden information even when it is as cold as physics allows. Nowhere does this truth become more profound than in the physics of gravity. Gravity is not just a force that pulls objects together. It is the curvature of space-time itself. When mass or energy exists, it bends space and time around it. This bending determines how everything moves. In this sense, space-time is not just a stage for physics. It is an active participant. When gravity is strong, it can trap information. Black holes are the ultimate example of this. A black hole can be extremely cold. The most massive black holes in the universe are colder than the faint radiation that fills space. Yet these same objects have more entropy than anything else known in physics. The entropy of a black hole is not stored in hot particles or chaotic motion. It is stored in the area of its event horizon. This area tells us how many different internal states the black hole could have. Every bit of matter that falls in adds to this count. The black hole becomes colder as it grows more massive, but its entropy increases. This shows that entropy does not require warmth. It requires structure. It requires the existence of many possible internal arrangements. When matter falls into a black hole, its information is not destroyed. It is encoded on the horizon in subtle quantum patterns. The black hole may appear simple from the outside, described only by its mass and spin, but on the inside it holds an enormous number of possible states. Its entropy is a measure of that hidden complexity. This leads to a radical idea. Gravity itself is a carrier of information. The geometry of space-time can store entropy. Even when all heat is gone, the universe can still be full of memory. The vacuum itself also carries entropy. Quantum fields fluctuate in countless ways. They become entangled across vast distances. These entanglements encode information even when temperature is 0 Kelvin. The vacuum is not empty. It is a web of relationships between fields that persist forever. As the universe cools and approaches its final state, entropy does not disappear. It changes where it lives. In the early universe, entropy was mostly in hot radiation and moving matter. In the far future, it will be in black hole horizons, in quantum fields, and in the geometry of space-time itself. This means that time does not end at absolute zero. Time is linked to the growth of entropy. As long as entropy can change, there is a distinction between past and future. In a cold universe, entropy still evolves because quantum states continue to fluctuate, and space-time continues to stretch. So even when heat is gone, the universe continues to have a story. It continues to remember what has happened. It continues to change in subtle ways. Absolute zero does not erase complexity. It reveals a deeper form of it. A universe of cold fields and curved space-time can be just as rich in information as a universe of fire and motion. Gravity becomes the keeper of that information. The vacuum becomes its medium. This is the true meaning of entropy at 0 temperature. When the universe grows cold, it does not forget. It remembers everything in the deepest layers of its structure, and gravity carries that memory forward into the endless future. When the universe approaches absolute zero and heat has almost entirely vanished, entropy does not fade away with it. Instead, entropy finds new places to live. It moves from the chaotic motion of particles into the quiet structure of quantum states and the deep geometry of space-time. To understand how this happens, we must look at the way information is stored in the universe when temperature is no longer the main driver of change. In a warm universe, entropy is carried by motion. Particles fly around. Radiation spreads. Energy flows from hot places to cold places. These processes scramble information and increase the number of possible arrangements of matter and energy. But when the universe cools and approaches 0 Kelvin, this kind of scrambling slows down. thermal motion becomes negligible. Yet the universe does not become perfectly ordered. Instead, it enters a regime where quantum mechanics and gravity take over as the main carriers of entropy. Quantum entanglement is one of the most important of these carriers. When two particles become entangled, their properties become linked, even if they are far apart. The state of one cannot be fully described without the other. This creates a form of hidden information that is not stored in any single place. It is stored in the relationship between particles. Even at 0 Kelvin, these relationships can exist. They do not depend on heat. They depend on the structure of quantum states. The vacuum itself is filled with entangled fields. Quantum fluctuations are not isolated events. They are connected across space. These connections store information. The vacuum at 0 Kelvin is therefore not simple. It is a vast network of entanglements that encode entropy in a form that does not look like disorder, but is just as real. Gravity plays a crucial role in this process. When space-time curves, it creates horizons. A horizon is a boundary beyond which information cannot be directly observed. Black hole horizons are the most famous example, but they are not the only ones. In an expanding universe, there are also cosmic horizons that limit what regions of space can communicate with one another. Every horizon has entropy. This entropy measures how much information is hidden behind the boundary. Even if the universe is cold, this entropy remains. It is tied to the geometry of space-time, not to the temperature of matter. This means that as the universe expands and cools, it may actually develop more entropy rather than less. More regions become isolated. More information becomes hidden behind horizons. The structure of space-time itself becomes more complex. In this cold future, entropy is no longer something you can feel as warmth. It is something you can only detect by studying the geometry of the universe and the patterns of quantum fields. Time continues to flow because these patterns continue to change. Even if nothing moves in the usual sense, the relationships between quantum states evolve. The expansion of space changes which regions can interact. Horizons grow and shift. Information is constantly being rearranged, so 0 Kelvin does not mark the end of thermodynamics. It marks the transition to a deeper thermodynamics, where gravity and quantum mechanics define how entropy behaves. In this regime, the universe becomes a silent but intricate tapestry of information. Gravity weaves the large-scale pattern. Quantum fields fill in the fine detail. Together, they ensure that the universe never becomes trivial even in its coldest state. As entropy migrates from heat into geometry and quantum relationships, the nature of time itself begins to change. In a warm universe, time is marked by the flow of energy. Hot objects cool, stars burn their fuel. Heat moves from one place to another. These processes give us a clear arrow of time. But in a universe approaching 0 Kelvin, those familiar processes fade away. What remains is a quieter but still powerful arrow driven by the evolution of space-time and information. Time is deeply connected to entropy. The direction of time is defined by the direction in which entropy increases. In a universe filled with heat, this increase is easy to see. But when temperature is near zero, entropy still changes. It just changes in subtler ways. The expansion of the universe creates new horizons. Regions that were once able to exchange information become separated. When that happens, entropy increases because information becomes hidden. The universe does not need heat to generate entropy. It only needs the growth of inaccessible regions of space-time. Quantum entanglement also evolves. Even in a cold universe, quantum fields continue to fluctuate. Their entanglement patterns change. These changes encode information. They create a flow of time that is invisible to ordinary thermometers, but real to the fabric of reality. Black holes also play a role in this deep cold era. A black hole can be extremely cold, yet it continues to have entropy, and it continues to evolve. As it slowly emits Hawking radiation, it loses mass. Its horizon shrinks. Its entropy changes. This is a process that can take longer than 10 to the power of 67 years. But it is still a process. Time still passes. So even at absolute zero, the universe does not become timeless. It continues to change in ways that are governed by gravity and quantum mechanics rather than heat. This means that the far future of the universe is not a frozen snapshot. It is a slow unfolding of geometry and information. Space continues to stretch. Horizons continue to form. Quantum fields continue to fluctuate. Entropy at 0 Kelvin is not about disorder. It is about possibility. It is about the number of ways the universe can be arranged at the deepest level. That number continues to change, even when everything is cold. So gravity and entropy become partners in shaping time. Gravity creates horizons and curvature. Entropy measures the information stored in those structures. Together they define the arrow of time in a universe without heat. In the far future of a universe that has cooled toward absolute zero, the familiar markers of time have disappeared. There are no clocks ticking in warm rooms. There are no stars burning their fuel. There is no heat flowing from one place to another. Yet time has not stopped. It has simply taken on a new form. That form is written into the expansion of space and the evolution of information. Every moment the universe grows larger. Distances between regions increase. New horizons appear that separate what can be known from what can never again be reached. Each of these changes increases entropy. It hides information. It creates new possible configurations of reality. This is the arrow of time in a cold universe. Quantum fields continue to fluctuate even when temperature is 0 Kelvin. Their fluctuations are not random noise. They are governed by precise laws, but they create an endless sequence of possible states. The universe is never locked into a single configuration. It is always exploring new ones. Gravity shapes this exploration. It determines how space curves and how horizons form. It defines what regions of the universe can communicate and which cannot. In doing so, it controls how entropy grows. So the cold future of the universe is not a static eternity. It is a slow unfolding of geometry and information. Even when everything is cold, the universe is still alive with change. At the deepest level, the story of entropy at 0 temperature is a story about memory. When heat fades and motion slows, the universe does not forget what it has been. It records that history in the structure of space-time and in the patterns of quantum fields that fill the vacuum. Every event that has ever happened leaves an imprint. When matter falls into a black hole, its information becomes encoded on the horizon. When space expands, it hides regions of the universe behind cosmic horizons. When quantum fields fluctuate, they create entanglements that link distant parts of space. All of these processes store information. All of them contribute to entropy. So even in a universe that has cooled to 0 Kelvin, entropy remains vast. It is no longer something you feel as warmth. It is something you see in the geometry of the cosmos. Gravity is the great archivist of this information. It bends space in ways that trap and preserve data. It creates horizons that store entropy. It shapes the vacuum so that quantum fields can carry memory across unimaginable distances. This means that the cold death of the universe is not a blank page. It is a book filled with everything that has ever happened, written into the fabric of reality. When temperature reaches 0 Kelvin, gravity does not fade. It becomes the last force holding the story of the universe together. Time does not belong to heat. This is one of the deepest truths modern physics has revealed. We are used to thinking that time is measured by clocks that tick and by processes that change, and many of those processes are driven by temperature. A warm cup of coffee cools. A hot star burns. A moving object slows. It feels as though time is tied to motion, and motion is tied to heat. But when physics looks beneath these familiar experiences, it finds that time is woven into something far more fundamental. Time is part of space-time, and space-time is shaped by gravity. When Albert Einstein developed the theory of relativity, he showed that space and time are not separate things. They are two aspects of a single fabric. When mass or energy is present, this fabric bends. That bending changes how objects move through space and how they move through time. This is why gravity affects clocks. A clock in a strong gravitational field runs more slowly than a clock far away. This effect is called time dilation. It has been measured with extraordinary precision, using satellites, atomic clocks, and observations of stars orbiting black holes. The important thing is that this effect does not depend on temperature. A clock placed on the surface of a cold neutron star would tick more slowly than a clock in empty space, even if both were at 0 Kelvin. A clock near a black hole would slow almost to a halt, regardless of how cold the environment is. Gravity controls time, not heat. To understand why this matters for a frozen universe, we must look at what happens to matter as it cools. When temperature drops, thermal motion fades, atoms vibrate less, molecules rotate more slowly. Eventually, at 0 Kelvin, all thermal motion disappears. Matter settles into its lowest possible energy states. But the mass of that matter does not disappear. Its gravitational influence remains. A white dwarf star may cool over billions of years until it becomes almost perfectly cold. Yet its gravity remains strong because its mass is still packed into a small volume. A neutron star may radiate away its heat and become dark and cold, but its gravity continues to bend space-time so strongly that time on its surface flows more slowly than time far away. These objects show that cold does not weaken gravity. It simply removes one form of energy while leaving the deeper structure untouched. Black holes are the most extreme example. The largest black holes in the universe are colder than the faint background radiation that fills space. They are colder than the cosmic microwave background. Yet their gravity is so strong that it traps light and warps space-time into deep wells. Near the event horizon of a black hole, time slows so much that from the outside, it appears to freeze. This happens not because the black hole is cold, but because its gravity is immense. So what happens to time in a universe that has cooled to absolute zero? It continues to flow, shaped by gravity and by the geometry of space-time. In the far future, the universe will be filled with cold remnants. White dwarfs will have cooled into black dwarfs. Neutron stars will be dark and silent. Black holes will slowly evaporate over spans of time that dwarf the age of the current universe. Yet throughout this long era, space-time will continue to curve and change. The vacuum itself will continue to influence time. The energy of empty space drives the expansion of the universe. As space expands, horizons form that separate what can be observed from what cannot. These horizons are a form of gravitational structure. They create an arrow of time because information becomes hidden behind them. Even in a cold universe, entropy continues to change, and that change defines the direction of time. Quantum fields also continue to fluctuate even at 0 Kelvin. Their fluctuations are not thermal. They are built into the laws of physics. These fluctuations create subtle changes in the vacuum. They contribute to the flow of time at the deepest level. So a frozen universe is not a timeless universe. It is a universe where the familiar signs of time, such as heat and light, have faded, but the deeper rhythms remain. Space-time continues to stretch. Horizons continue to form. Information continues to evolve. Gravity is the engine of this frozen time. It bends space-time. It creates the conditions under which moments have meaning. Even when everything is cold, gravity ensures that the universe continues to have a past and a future. This is the quiet truth about time at absolute zero. The universe may lose its warmth, but it never loses its story. When the universe becomes deeply cold, the way time reveals itself changes. But time does not disappear. The fading of heat removes the most obvious signs of motion. Yet the deeper mechanisms that create the flow of moments continue to operate. To understand this, it is necessary to see time not as something measured by clocks, but as something written into the geometry of space-time itself. Gravity does not simply pull objects together, it reshapes the very fabric through which all motion occurs. In Einstein's view of the universe, space and time are woven together into a single structure. This structure bends in response to mass and energy. Where the bending is strong, time runs slowly. Where the bending is weak, time runs more quickly. This relationship is absolute. It holds no matter how cold the universe becomes. Imagine a neutron star that has cooled over billions of years until it emits almost no heat. Its surface may be colder than any laboratory on Earth could ever achieve, yet its gravity remains enormous. The curvature of space-time around it is so intense that time on its surface runs much more slowly than time far away. If a traveler could somehow stand on that frozen star and look out into the universe, they would see distant galaxies evolving at a speed far faster than their own local clock. This time dilation exists because gravity warps space-time, not because of temperature. Cooling the star removes thermal energy, but leaves its mass untouched. The geometry of space remains curved, and time remains stretched. The same principle applies to black holes. The largest black holes in the universe are colder than the faint background radiation that fills space. They are among the coldest objects that exist. Yet they also create the strongest time distortions known. Near a black hole, time slows to a crawl. At the event horizon, from the perspective of a distant observer, time nearly stops. This happens not because the black hole is cold, but because its gravity is overwhelming. So even in a universe that has reached absolute zero, regions of strong gravity will still experience slower time than regions of weak gravity. The frozen cosmos will still contain a landscape of time dilation shaped by mass and energy. The expansion of the universe adds another layer to this story. Space itself is stretching. This stretching does not require heat. It is driven by the energy of the vacuum. As the universe expands, new regions of space come into existence. This changes the geometry of space-time and creates an arrow of time on the largest scales. As space grows, horizons form. These horizons mark the limits of what can ever be observed. Regions that were once in contact become permanently separated. Information becomes hidden. This increase in hidden information is entropy, and the growth of entropy defines the direction of time. Even at 0 Kelvin, entropy continues to grow through the formation of horizons and the expansion of space. The universe continues to move forward. Quantum fields also ensure that time never stops. Even when all matter is cold and still, quantum fluctuations persist. These fluctuations create an endless sequence of microscopic events. They are not driven by heat, but they are real changes in the state of the universe. As long as these changes occur, time has meaning. So the frozen future of the universe is not timeless. It is a slow and subtle evolution of geometry, information, and quantum states. Gravity shapes how quickly different regions experience this evolution. The vacuum drives the expansion that gives time its cosmic direction. Absolute zero removes warmth, but it cannot remove the flow of moments written into spacetime itself. As the universe continues its slow descent toward deeper cold, the experience of time becomes increasingly shaped by the large-scale structure of spacetime, rather than by local physical processes. In the early universe, time was easy to feel. Stars were being born and dying. Galaxies were colliding. Radiation was flowing from one place to another. These energetic events created a sense of rapid change. But in the far future, when the universe has cooled towards 0 Kelvin, such dramatic events become rare, yet time does not vanish. It simply reveals its deeper form. Gravity remains the dominant sculptor of time. Wherever mass and energy exist, space-time curves. That curvature determines how moments unfold. Even if a star has cooled to a dark remnant, its mass still warps space-time. A white dwarf that has radiated away almost all of its heat continues to slow time near its surface. A neutron star that has grown cold still bends space-time so strongly that clocks there tick far more slowly than clocks far away. Black holes show this most clearly. Even when a black hole is colder than the surrounding universe, it remains a region where time is profoundly distorted. Near the event horizon, time slows to such an extent that, from the outside, nothing ever truly crosses it. This is not because the black hole is hot or cold. It is because space-time itself has been bent into an extreme shape. As black holes slowly evaporate through Hawking radiation, their mass decreases. This changes the curvature of space-time around them. The way time flows near them evolves. Even in the coldest era, the universe continues to experience change through these processes. The expansion of space also continues to shape time. Vacuum energy stretches the universe. As distances grow, new horizons form. Regions that were once close become forever separated. This creates a growing network of boundaries that limit the flow of information. Every such boundary increases entropy. Every increase in entropy marks the passage of time. Quantum fields continue to fluctuate as well. Even at 0 Kelvin, these fields are never still. Their fluctuations are not thermal, but they are real. They represent an ongoing sequence of micro-events that give time its fine structure. So in the frozen universe, time is written in the slow unfolding of geometry and quantum activity. There may be no fire and no motion that we can easily see, but space-time itself continues to evolve. This is the quiet but relentless heartbeat of a cold cosmos. When the universe reaches the deep cold of its far future, time does not vanish. It changes in character, becoming something far more subtle and yet far more profound. In a young and energetic cosmos, Time is easy to recognize because events happen quickly. Stars ignite, galaxies collide, matter flows, and radiation fills space. These processes give us obvious markers of change. But in a frozen universe, where temperature approaches absolute zero, these dramatic signs fade. What remains is a quieter, slower, and deeper form of time, driven by gravity and the structure of space-time itself. To understand how time continues in such a cold universe, it is important to remember that time is not something that exists independently. It is part of space-time, a fabric that is shaped by mass and energy. Even when matter loses all thermal motion, it does not lose its mass. And as long as mass exists, space-time remains curved. This curvature determines how time flows. A cold neutron star still bends space-time just as strongly as a hot one. A cold black hole still creates an extreme distortion of time near its horizon. These objects do not lose their gravitational influence when they lose their heat. So even in a universe that has cooled to absolute zero, time will not be uniform everywhere. Some regions will experience time more slowly, others more quickly, depending on the curvature of space-time around them. In the far future, most ordinary matter will be gone. Stars will have burned out. Their remnants will have cooled into dark and silent objects, but black holes will remain for extremely long periods. These cold black holes will continue to warp space-time. They will continue to slow time near their horizons. They will remain islands of strong gravity in an otherwise empty universe. As black holes slowly evaporate through Hawking radiation, their mass decreases. This changes the curvature of space-time around them. As their mass shrinks, the distortion of time they create becomes weaker. This means that even in a cold universe, the flow of time continues to change as black holes evolve. Time is not static. It is shaped by the slow transformation of gravity. The expansion of the universe also plays a central role. Vacuum energy drives space to expand faster and faster. This expansion does not require heat. It continues even when temperature is near zero. As space expands, the distances between all remaining objects grow. Regions that were once close become separated by enormous gaps. This expansion creates cosmic horizons. A horizon is a boundary beyond which light and information can never reach an observer. As the universe expands, more and more of reality slips beyond these horizons. Each new horizon hides information. Hidden information is entropy, and the growth of entropy gives time its direction. So even when the universe is frozen, entropy continues to increase because space continues to expand and create new horizons. This means that time still has an arrow. The future is still different from the past. Quantum mechanics also ensures that time continues. Even at 0 Kelvin, quantum fields fluctuate. These fluctuations are not caused by heat. They are built into the laws of physics. They create a continuous sequence of microscopic changes. As long as these changes occur, the universe is not static. In a cold universe, time becomes something that is measured not by fire and motion, but by geometry and information. The shape of space-time changes, horizons grow, quantum states evolve. These processes define the passage of moments. So the far future of the universe is not a timeless void. It is a slow and silent evolution of space, time, and information. Gravity remains the great architect of this evolution. It shapes the flow of time even when everything is cold. This is the deep truth about time and frozen matter. Cold does not stop the universe. It reveals the most fundamental rhythm of reality. In the final epochs of the universe, when temperature has fallen so close to absolute zero that even the faint glow of ancient radiation has nearly vanished, time does not come to an end. Instead, it becomes something far more subtle and profound. What remains is not a frozen snapshot of reality, but a slow and continuous evolution of space-time, information, and gravity. At this stage, almost all ordinary matter has faded. Stars have burned their fuel. White dwarfs have cooled into dark remnants. Neutron stars have lost their heat. Black holes have spent unimaginable spans of time slowly evaporating. Yet even as these familiar structures disappear, space-time itself continues to change. The vacuum of space is never empty. It contains quantum fields that fluctuate even at 0 Kelvin. These fluctuations do not produce warmth, but they do produce energy. That energy bends space-time. It contributes to the overall gravitational structure of the universe. As long as the vacuum exists, gravity exists. The expansion of space continues as well. Driven by vacuum energy, the universe keeps growing larger. This expansion creates ever more distant regions that can never again communicate. These horizons represent lost information. As information becomes hidden, entropy increases. The growth of entropy gives time its direction, even when there is no heat. So in a frozen universe, time is written into the expansion of space and the evolution of horizons. It is written into the slow drift of quantum states. It is written into the changing geometry of space-time. Gravity remains the central force behind all of this. It shapes how space-time curves. It determines how fast time flows in different regions. It governs how information is stored and hidden. When heat is gone and motion is quiet, gravity still guides the universe forward. Time continues, not because of fire or warmth, but because the fabric of reality itself is still evolving. This is the ultimate answer to what happens to time when the universe grows cold. Time does not freeze, it transforms, and gravity ensures that the story of the cosmos continues, even in the deepest cold. In the far future of the universe, a time so distant that even the longest-lived stars have faded into memory, the cosmos enters an era that seems at first glance like the ultimate ending. Light has nearly vanished. The glow of galaxies that once filled the sky has stretched into invisibility. The background radiation left over from the birth of the universe has cooled to almost nothing. Space is vast, dark, and silent. This state is often called the heat death of the universe, but that phrase hides what is really happening. The universe does not die. It changes into something quieter and more subtle than anything that came before. Temperature is the measure of motion. When something is hot, its particles move rapidly. When it is cold, they move slowly. In the distant future of the cosmos, almost all motion has faded. Radiation has lost its energy as it stretches across expanding space. Matter has clumped into a few remaining structures, and much of it has been swallowed by black holes. What remains is a thin mist of particles drifting through a vacuum that seems empty but is not. Even in this deep, cold, gravity still rules. Every particle, no matter how small, still bends space-time. Every black hole, no matter how cold, still creates a deep well in the geometry of the universe. The cosmos may no longer be filled with blazing stars, but space-time is still curved, and time is still shaped by gravity. Black holes are the last great structures of this era. Long after stars have burned out and planets have frozen, black holes remain. They can be colder than the surrounding space, yet their gravitational pull is overwhelming. They hold onto matter, light, and even time itself. Around them, space-time is twisted and warped. Even in a cold, dead universe, these objects create islands of intense gravity. Over unimaginable spans of time, black holes slowly evaporate through Hawking radiation. This radiation is extremely weak and extremely cold. It takes longer than 10 to the power of 67 years for a stellar mass black hole to fade away. For the largest black holes, the time is far greater. But even during this slow fading, gravity continues to shape the universe. As a black hole loses mass, the curvature of space-time around it changes. Time itself flows differently as a result. Beyond the black holes, the vacuum dominates. Space itself is filled with quantum fields that never turn off. These fields fluctuate even at 0 Kelvin. Their energy drives the expansion of the universe. As space expands, distances grow, and galaxies slip beyond one another forever. Horizons form that separate regions of the cosmos. Information is hidden behind these boundaries. Entropy continues to grow. So the cold, dead universe is not empty. It is structured by gravity and vacuum energy. It is quiet, but not simple. It is the final stage of a story that began with fire and ends with geometry. This is the universe when heat has almost vanished, a place where gravity remains the last force holding reality together. As the universe continues its long descent into deep cold, the remaining structures become ever more isolated. The distances between galaxies grow so vast that even the fastest light can no longer bridge them. Each region of space becomes a lonely island drifting through an ever-expanding sea of vacuum. The cosmos feels empty, yet it is still shaped by powerful forces that never truly disappear. Gravity continues to operate, even in this cold and quiet era. Any remaining mass, no matter how small, still bends space-time. A single particle drifting through the void creates a tiny curvature around itself. Black holes, though slowly fading, remain the dominant sources of gravity for unimaginably long periods. They shape the motion of anything that comes near them. They slow time. They trap information. As black holes evaporate, their mass is converted into radiation that spreads into the vacuum. This radiation is extremely weak and cold, but it still carries energy. That energy still curves space-time. The geometry of the universe evolves as black holes slowly give up their mass. The vacuum itself becomes more and more important. Its energy density does not fade as space expands. As more space comes into existence, there is more vacuum energy. This causes the expansion of the universe to accelerate. Even in a universe that is nearly at absolute zero, space continues to stretch faster and faster. This expansion creates horizons. These horizons mark the boundaries of what can ever be observed. Regions of the universe slip beyond one another and can never again exchange information. Each new horizon hides more of the cosmos. This increase in hidden information is entropy. It continues to grow even when heat is gone. So the cold, dead universe is not static. It is changing in a slow and subtle way. Space-time is stretching, horizons are forming, black holes are fading, quantum fields are fluctuating. Time continues to flow. It is no longer marked by fire and motion, but by the evolution of geometry and information. This is the strange final era of the cosmos. A universe without warmth, but not without gravity. In the farthest reaches of time, the universe becomes a place so vast and so empty that the concept of distance itself begins to lose meaning. Expansion has stretched space-time until every remaining structure is separated by distances so great that no signal can ever cross them. Light itself, no matter how long it travels, can no longer bridge the growing gaps. Each region of the cosmos becomes its own private universe, drifting alone through an ocean of expanding vacuum. This isolation is not the result of heat fading. It is the result of gravity in its most subtle form. The energy of the vacuum drives the expansion of space. As space grows faster and faster, regions slip beyond one another. Horizons form that permanently block communication. Even if two particles were once close together, they can be carried so far apart that they will never interact again. Yet gravity has not disappeared. It has simply changed its role. Instead of gathering matter into stars and galaxies, gravity now governs the geometry of the universe itself. It determines how fast space expands. It shapes the horizons that define what can be known. Black holes remain the last great monuments of the earlier universe. Long after stars have vanished and matter has decayed, these cold giants still exist. They may be colder than the surrounding space, yet their gravitational influence is overwhelming. Around each black hole, space-time is deeply curved. Time flows more slowly near their horizons than far away in the nearly empty void. As black holes slowly evaporate through Hawking radiation, their mass decreases. This changes the curvature of space-time around them. The geometry of the universe evolves in response. Even this incredibly slow process counts as change. It gives time a rhythm, even in a cold, dead universe. The radiation released by evaporating black holes spreads into the vacuum. It becomes ever more diluted as space expands, but it still carries energy. That energy still curves space-time. Nothing is ever truly removed from the gravitational story of the cosmos. Beyond the black holes, the vacuum dominates. Quantum fields fluctuate. Their energy drives the continued expansion of the universe. New regions of space come into existence. More horizons form. More information becomes hidden. Entropy grows, even when temperature is almost zero. So the cold, dead universe is not a simple emptiness. It is a place where gravity and quantum mechanics still rule. It is quiet, but it is not finished. The story of space-time continues even when everything else has faded. As the universe continues to expand into its deepest future, the meaning of distance and connection changes completely. What once were galaxies, once bound together by gravity, are now separated by unimaginable gulfs of empty space. The expansion driven by vacuum energy has carried them so far apart that no signal can ever pass between them again. Each region becomes a lonely island of space-time, drifting in a sea of growing emptiness. Yet this emptiness is not nothing. It is filled with quantum fields that never go quiet. Even at 0 Kelvin, these fields fluctuate. They contain energy. That energy bends space-time. The vacuum itself becomes the dominant source of gravity in the universe. This form of gravity does not pull objects together. It stretches space apart. As more space comes into existence, there is more vacuum energy. The expansion accelerates. Horizons form that hide ever larger portions of the cosmos. Black holes continue to exist for unimaginably long times. They are cold, yet they are still powerful. Their gravity still warps space-time. They still slow time near their horizons. They still store enormous amounts of information in their event horizons. As black holes slowly evaporate, their mass is released into the vacuum. This energy changes the curvature of space-time. The universe responds. Even this faint radiation becomes part of the gravitational story. So even in a cold, dead universe, gravity never leaves. It simply takes on new forms. It becomes the shaping force of space itself. In the final state of the universe, when all warmth has faded and nearly all matter has disappeared, what remains is a vast, quiet, and endlessly stretching fabric of space-time. It is easy to imagine this as true nothingness, but in reality, it is one of the most active and complex states the universe can reach. The cold, dead universe is not an empty void. It is a universe ruled by gravity and the vacuum. Even when stars, planets, and black holes are gone, space itself still contains energy. The quantum fields that fill the vacuum continue to fluctuate. Their energy continues to bend space-time. This bending drives the expansion of the universe and creates horizons that divide the cosmos into isolated regions. These horizons store information. They carry entropy. As the universe expands and more of reality slips beyond reach, entropy increases. Time continues to have direction. So the end of heat is not the end of the universe. It is the beginning of its quietest and longest chapter. A chapter where gravity and the vacuum remain as the last forces shaping everything that exists. This is the cold, dead universe. A place without warmth, but not without structure. In the farthest future of the universe, there comes a time when fire is only a memory. Stars that once blazed with unimaginable power have long since exhausted their fuel. Galaxies that once glowed across the sky have drifted beyond one another until their light can no longer cross the widening distances of space. The faint background radiation left over from the birth of the cosmos has been stretched by expansion until it carries almost no energy at all. Temperature has fallen closer and closer to 0 Kelvin. The universe has become cold beyond any ordinary meaning of the word. To the human imagination, this feels like the end of everything. We associate life and motion with warmth. We associate stillness with cold. It seems natural to think that when the universe becomes completely cold, it must also become completely dead. But physics reveals something far more strange and far more profound. When heat fades, the universe does not lose its structure. It reveals its deepest one. Heat is only one way energy can appear. In the early universe, energy existed mostly as radiation and hot matter. Those forms created the stars, the galaxies, and the light that filled space. But as the universe expanded, that energy spread out. It became diluted. Stars burned through their fuel. Radiation lost its power. Eventually, almost all of the energy that once drove visible motion disappeared. But energy itself did not disappear. The vacuum of space still contains energy. Quantum fields fill every region of the universe. These fields do not depend on temperature. They do not cool or freeze. Even at 0 Kelvin, they fluctuate. Tiny ripples move through them. Virtual particles appear and vanish. This restless activity is not heat, but it is real energy. And wherever there is energy, there is gravity. Gravity is not something that runs on fuel. It is not something that needs heat to exist. It is the geometry of space-time responding to energy. When energy is present, space-time curves. That curvature determines how objects move and how time flows. This means that even in a universe that has cooled to absolute zero, gravity remains. Space-time is still bent by the energy of the vacuum. The universe continues to expand. Horizons continue to form. The shape of reality continues to change. Black holes become the last great monuments of this cold era. They are among the coldest objects in existence, yet their gravity is overwhelming. Around them, space-time is twisted into deep wells. Time slows near their horizons. Light is trapped. Information is stored. These objects may emit almost no heat, but they dominate the geometry of the universe. Over unimaginable spans of time, black holes slowly evaporate through Hawking radiation. This radiation is extremely weak and extremely cold. It takes longer than 10 to the power of 67 years for a typical black hole to fade. Yet even this slow process is part of the story of gravity. As black holes lose mass, space-time slowly changes shape. Time itself flows differently as a result. So even in the coldest possible universe, nothing is truly frozen. Space-time continues to evolve. Gravity continues to shape reality. The cosmos still has a future. This is the final truth about absolute zero. It does not erase the universe. It strips away everything except the most fundamental forces. When heat is gone and motion is quiet, gravity remains as the last force holding reality together. As the universe continues its long journey into deep cold, the familiar forms of energy that once filled space fade into memory. In its youth, the cosmos was ruled by heat. Stars were powered by nuclear fire. Galaxies glowed with radiation. Clouds of gas moved and collapsed under the combined influence of gravity and thermal pressure. Heat determined what could happen and how fast it could happen. But as the universe expanded and cooled, this regime slowly came to an end. When heat disappears, something remarkable happens. The forces that once opposed gravity weaken. Thermal motion no longer pushes matter outward. Radiation no longer provides pressure. What remains is gravity acting almost alone. This is why the coldest objects in the universe are also the densest. White dwarfs and neutron stars are supported not by heat, but by quantum rules that prevent particles from occupying the same state. These rules create pressure even when temperature is zero. As these stars cool, their thermal energy fades, but their quantum pressure and gravitational structure remain. They do not collapse because of warmth. They exist because of the deep laws of physics. Black holes represent the final stage of this process. A black hole has no internal structure that depends on heat. Its temperature is determined only by quantum effects at its horizon. The more massive a black hole becomes, the colder it is. Yet at the same time, its gravity becomes stronger. This reveals a profound truth. Gravity and temperature are not linked in the way we might expect. Extreme cold does not weaken gravity. It allows gravity to dominate. As the universe ages, black holes become the last massive structures. They absorb what little matter remains. They curve space-time more strongly than anything else. They slow time near their horizons. They store information about everything that has ever fallen into them. Over unimaginable spans of time, black holes slowly evaporate. Their Hawking radiation is extremely faint and extremely cold. It takes longer than 10 to the power of 67 years for a typical black hole to fade. Yet even during this slow evaporation, gravity continues to shape the universe. As mass is lost, space-time slowly changes shape. Time itself flows differently as a result. Beyond the black holes, the vacuum dominates. Quantum fields fill space. Their energy drives the expansion of the universe. This expansion is a gravitational phenomenon. It is space-time responding to the energy of the vacuum. Even when temperature is zero, the universe continues to grow. So the final universe is not one where gravity has faded. It is one where gravity has become the only force left. In the final epochs of the universe, when the background temperature of space has fallen so close to absolute zero that it is effectively frozen, gravity emerges as the only remaining sculptor of reality. Every other force that once shaped the cosmos has faded into silence. Heat no longer moves matter. Radiation no longer fills space with light. Yet gravity continues, quietly and relentlessly, guiding the evolution of space-time itself. This happens because gravity is not tied to temperature. It is tied to the existence of energy and mass. Even when matter decays and radiation thins out, energy remains in other forms. The vacuum itself contains energy. Quantum fields fluctuate. These fluctuations are not thermal, they are fundamental. and because they carry energy, they curve space-time. So in the cold future of the universe, space-time is still not flat. It still has shape. It still changes. Black holes play a central role in this era. They are the last great reservoirs of mass and information. They may be colder than the surrounding space, yet they dominate the gravitational landscape. Around each black hole, space-time is warped into a deep well. Time slows near their horizons. Even light struggles to escape. As black holes slowly evaporate through Hawking radiation, they lose mass. This radiation is extremely faint and extremely cold, but it carries energy. That energy spreads into the vacuum and continues to curve space-time. Nothing ever escapes the influence of gravity. As black holes fade, the geometry of the universe changes. The deep wells they created become shallower. Time flows more evenly across space, yet the vacuum continues to drive expansion. Space grows larger. Horizons form that separate regions of the cosmos. Information becomes hidden. Entropy increases. These processes ensure that even a universe at 0 Kelvin is not static. It continues to evolve. Gravity writes the final chapter of cosmic history in the slow shifting of space-time itself. When heat has died, gravity remains. It becomes the last force holding the universe together and guiding it forward into an endless future. In the deepest future of the universe, when every trace of warmth has faded and the background temperature of space has fallen to almost absolute zero, gravity stands alone as the final architect of reality. Long ago, the cosmos was filled with fire. Stars blazed, galaxies shone, and radiation flooded space. But expansion diluted that energy. Heat spread thinner and thinner until it could no longer drive the grand structures of the universe. Yet even as warmth disappeared, the universe did not become empty or inert. What remained was the geometry of space-time itself, shaped forever by gravity. Gravity is not something that depends on heat. It is not powered by temperature. It is powered by the existence of energy in any form. Whether that energy exists as glowing plasma, moving particles, or silent quantum fields, it curves space-time. That curvature tells everything how to move and how time should flow. As the universe aged, matter gradually fell into colder and denser forms. White dwarfs cooled, neutron stars darkened, black holes absorbed what little mass remained. These objects became colder and colder, yet their gravitational influence remained just as strong. A black hole with the mass of 1 billion suns is colder than the faint radiation that fills space. Yet its gravity is so intense that it can trap light and slow time to a crawl. This reveals a fundamental truth. Gravity and temperature are not linked in the way people imagine. The coldest objects can be the most powerful. Eventually, even black holes are not permanent. Over immense spans of time, they slowly release their mass through Hawking radiation. This radiation is unimaginably weak and cold. It takes longer than 10 to the power of 67 years for a typical black hole to fade away. Yet during this long process, gravity continues to shape the universe. As each black hole loses mass, the curvature of space-time around it changes. The way time flows near it changes. Even in a cold universe, the geometry of reality continues to evolve. Beyond the fading black holes, the vacuum dominates everything. Space itself contains energy in the form of quantum fields. These fields never stop fluctuating, even at 0 Kelvin. Their energy is not thermal, it is built into the laws of physics. Because this energy exists everywhere, it has a powerful gravitational effect. It causes space to expand. As space expands, more vacuum energy appears. This drives the expansion even faster. This expansion creates horizons. These horizons mark the limits of what can ever be observed. As they grow, more of the universe slips beyond reach. Information becomes hidden. Entropy increases. Time continues to move forward. So the cold future of the universe is not a frozen ending. It is a slow unfolding of geometry and information. Gravity remains the force that shapes this unfolding. It bends space-time. It governs the expansion of space. It determines how time flows in different regions. When heat fades, gravity does not disappear. It becomes the last force holding the universe together. In the farthest future that physics allows, when every star has long since burned out and even the faintest remnants of radiation have been stretched thin by the expansion of the universe. Reality enters a state that is colder and quieter than any era that came before. The background temperature of space approaches absolute zero. Heat, once the great engine of cosmic change, no longer drives anything. There are no warm worlds, no glowing clouds of gas, and no shining galaxies. To any observer, if such an observer could still exist, the universe would appear almost completely empty. But emptiness is not nothingness. Beneath this silence, gravity still speaks. Gravity is not a force that depends on warmth. It is not sustained by fire or motion. It is woven into the fabric of space-time itself. Wherever energy exists, space-time curves. Wherever space-time curves, gravity acts. Even when matter is gone and radiation has faded, energy remains in the form of the vacuum. Quantum fields fill all of space. They fluctuate endlessly, even at 0 Kelvin. These fluctuations carry energy. That energy bends space-time. So in the coldest possible universe, gravity does not disappear. It becomes the dominant feature of reality. The vacuum energy that fills space is subtle, but it is everywhere. As space expands, there is more vacuum, and therefore more vacuum energy. This causes the expansion of the universe to accelerate. The cosmos does not slow down as it cools. It grows larger and emptier. Regions of space are carried farther and farther apart. Horizons form that mark the limits of what can ever be seen. Information is hidden behind these boundaries. Entropy continues to increase. Time continues to flow because entropy continues to grow. Even without heat, the universe still has a direction. The future is still different from the past. Gravity and the vacuum together create this arrow of time. Black holes play a final and profound role in this story. Long after every star has vanished, black holes remain. They are among the coldest objects in the universe, yet they are also among the most powerful. Their gravity is so strong that it traps light and bends time. Near a black hole, seconds stretch into eternities. This happens not because the black hole is hot, but because space-time itself is deeply curved. As black holes slowly evaporate through Hawking radiation, their mass is released back into the vacuum. This radiation is extremely weak and extremely cold, but it still carries energy. That energy still curves space-time. Even the fading of black holes becomes part of the gravitational story of the universe. Over times longer than 10 to the power of 67 years, black holes slowly disappear. But even when the last black hole has faded, the universe does not become empty. The vacuum remains. Its fields continue to fluctuate. Its energy continues to shape space-time. Expansion continues. Horizons continue to form. This means that gravity survives the death of heat. It survives the death of stars. It survives the death of matter itself. As long as energy exists in any form, gravity exists. In this final universe, reality is no longer defined by fire or motion. It is defined by geometry. The shape of space-time determines how everything behaves. Time flows according to curvature. Distance grows according to vacuum energy. Information is stored in horizons and quantum fields. This is the ultimate fate of the cosmos. Not a sudden end, but an endless quiet evolution, guided by gravity alone. When heat fades, when motion stills, and when the universe grows cold beyond imagination, gravity does not disappear. It becomes the last force holding reality together.